Okay. Hello, everyone. I'm Musanna. I'm a PhD candidate at UBC Vancouver. Recently I got a award or grant, whatever we'd like to say, from Digital Research Alliance of Canada. On My proposal was to build a pre and post-processing tool, which I named AtomProNet, which is the short form of Atomic Data Processing for Neural Network, which will help researchers from different field to use machine learning, especially for atomistic simulation. I know maybe it's not familiar to some of the audience's skill set, but I think to get a broader view how the atomistic simulation works will maybe eventually work somehow in your research also. So yeah, so that's the idea for today. That will first of all I'll show a short presentation, and after that we'll go through like a hands-on tutorial session to build an interatomic potential so that we can run some simulation with it and get some data. So the contents are that first I'll give a brief introduction about MLIPs, which is the short form of Machine Learning Interatomic Potential. I'll have a survey to complete. I hope everybody will help me to complete the survey, and then I'll have the tutorial, which will be in a few parts, and the question answers. So the requirements is that if you have the if you have the background on DFT, MLIP, that's good. But if you don't have, that's totally fine. We'll go through each step. And we'll try to actually understand what's going on here, and you can catch up it later if you want to do MLIP simulations. Okay, this plot, what it gives information is that if you look here, these are cubic scaling. If we do DFT, quantum mechanics, and if we increase the number of atom, the number of electron will also increase, and it will scale cubic scaling. But if we want to study a system which will have millions of atoms, it's not possible to go for cubic scaling. It will be computationally so expensive that we cannot go for that. So we need something with linear scaling. For the purpose of linear scaling, the idea of potential energy surface came. So basically, if we know the energy landscape of a system, it could be any system, any material, silicon dioxide, any battery materials. If we can know that energy landscape, we can get the energy from there. And then just a second, I'll just, yeah. Energy landscape, we can get the energy from there, and we can take the derivative of that energy to get the forces and stresses involved in it. Before the implementation of machine learning, people used to do optimization technique, but right now technique like graph convolution on the atomic structure is used in this purposes. So basically, we can take a graph of the atom, we can represent the atomic structure with a graph, then we can calculate the energy, and then from there we can take the derivative to calculate the forces. One more important thing I'd like to mention, let's say we have a dice. Now we want to include all of the features of that dice when it rotates in different orientation. But think about it, if we try to explicitly add it, there could be thousands of different orientation we need to add, and we might miss some of them. It's not possible to add all of them. But if we can add the symmetry parameters in it, then we'll be able to capture this feature without having all of them explicitly. So based on these, there are different kind of interatomic potentials available. I'll not go through the different kind of potentials, but we can divide them into two categories. One is invariant model, and the another is equivariant model. So in the invariant model, if you rotate the structure, the values will not change. It will just stays the fixed values. But for the equivariant model, if you rotate the structure, the energy value will be fixed, but the forces will change accordingly to make the system balanced. So I would show some example before going to the tutorial. For example, here what you are seeing is that I have an alumina structure, and there is a void in that structure. So with time, if we add loading on it, especially hydrostatic loading, this structure will break. Now, this is the alumina structures will break through crack bifurcation. But what you are seeing here is that Allegro is capturing this crack bifurcation. COMB and ReaxFF are not capturing this in such a high level. And here it's a 20 by 20 nanometer structure with 1 million atoms in it. And this Allegro is basically a machine learning interatomic potential. So these are few results what we got from the machine learning interatomic potential. And this is a stress strain plot. And this stress strain plot is closer to the experimental result also. So this gives us an information that if we can train a model with good quality data, in machine learning, it can give us a machine learning interatomic potential that can be used to study the physics of a problem. So how did I build this model? So I did some DFT simulations of the strain system. Here you can see that I'm adding hydrostatic level in the DFT system. I took this data and that I trained in an equivariant neural network. And then from there, I get the MLIP, and then I can run this kind of simulation. So for battery field, we know that we deal with different kind of complex material. There are so many atomic element in it at different compositions. So I think the future will be to study the battery system in atomistic scale, that will be using machine learning interatomic potential more frequently to study problem like ionic movement, dendrite formation, and SEI formation, in which area this kind of technique will be very useful to implement. Okay, now how do we validate a machine learning interatomic potential? So there are different ways. One of the way I'm showing here is that we get the true energy. So the true energy is the actual baseline energies that we can get from DFT or any other quantum mechanics method. And the predicted energies is the energies that we predict through the machine learning interatomic potential. So as you can see here is that the higher the value of the R square and the dots are closer to the red line, that means that the predicted and the true energies are close to each other. This is one way to validate it. Another way could be the cumulative distribution. So for example, if we look here in the energy error plot, so what we are seeing here that 0.05, so 95% of the atomic energies are lower than the energy of 0.05. And similarly for the forces of different system. So for this simulation, what I used 16,000 DFT structure. I split them into training, test, and validation set, and then I got this nice MLIP. One parameter which is not fully considered, I would say, when people develop machine learning atomic potential, once you build it and once you try to implement it to solve a problem, how the performance goes. So that's why we did some benchmarking for molecular dynamics to see if we increase the cell size, how it performs. So here Allegro and MACE, these are two machine learning interatomic potential, and the COM3 and REACT is the classical optimization based interatomic potential. So what we are seeing is that the MLIPs are performing better than the classical interatomic potential, but given the fact that we are not using the charge equilibration in each step. So this is something which we are focusing on our paper also. Now let's coming to the point of how to build an interatomic potential. First of all, we need a data set. So now there are different databases available readily. For example, Material Project, we can go there. We can download lithium battery material, lithium cobalt oxide, and then we can use that database, and then we can define a descriptor. We can take an architecture, and then we can build the machine learning interatomic potential. So starting from 2007, researchers started doing different kind of descriptor. So descriptor is basically how do you define the atomic structure? How do you define the atoms? How they interact with each other? There are different kind of methods. To recently is graph-based descriptor, what we described in the first slide. After that, we go for the architecture. Mostly all of them are short range, but currently researchers are working on how to include the long range effect. That means like if some effect happen or a defect or something like that, some deposition happen in a further away from the atomistic structure, we are thinking about within the certain cutoff radius, how that affects on that atomistic structure within that cutoff radius. So now we'll show you the MedBench Discovery. This is a benchmarking platform. Let's look at first on the leftmost column. So it shows different kind of atomic potential name. And if you look at the rightmost column, what you will see is that every few months we are getting a new interatomic potential. So this field is moving very fast, and it's very difficult to keep track with all the new developments that are going on. So that's why if we can come up with a generalized pre and post processing tool through which we can implement any of the model easily, that would be the ideal case scenario. Even for the experimentalist, they will be able to use it easier without knowing the background of it. So for today, what we'll do is that we'll focus on MACE. This is an equivalent interatomic potential. We'll try to build an interatomic potential with these, and then we'll try to even try to run a MD simulation with it. Okay, so this is the architecture of AtomProNet. There are 4 modules. The first one is we'll download the structure, then we'll submit some job, DFT job. Then we'll check the convergence if the jobs are well minimized or not. After that, we'll collect those data, information like energy, forces, position, lattice parameter, and stresses. Once we do this, we'll build the interatomic potential using MACE, and then we'll try to validate and see how the results look like. I'll stop my presentation here. Uh, yeah, we'll come back here later for the survey, but before going to the tutorial, is there any question from the audience? Okay, if no, so now what we'll try to do, we'll try to run this Colab tutorial. I will share the link if somebody wants to uh, play with it with me. I'll just share it in the chat. Okay. Yeah. So as I said, like there are 4 modules. First, we have to install the software, then we can download the data from the material project, then we can run DFT simulation, then we can extract the data from DFT simulation for neural network training, and then we can do the post-processing. So I'll start with the installation. First, what we have to do is that close. So we should change the runtime because we are doing a machine learning training. So we should change the runtime to GPU because if we only use CPU, the training will be very slow. So once we do this, we change the runtime. We click this cell, run anywhere, and then it will start installing all the required packages for this software. So it will take maybe 30-40 seconds to install. So once it is installed, we'll be able to see a new folder here, which is called AtomProNet. And we can go inside the folder. We'll be seeing different things, but we'll be more focused on the example dataset. So under this example dataset, I already given some example completed data through which we can work and we can try to see what's going on there. So for now, I'll wait for a few seconds to install this software, and feel free to ask me any question if you are trying to run this Colab tutorial. Just follow what I'm doing, and let me know if you have any questions or if you face any difficulties.
About if you are interested to do, teach, I guess, repeat to some.
Or if you are not in the Zoom session, what you can do is that you can just write AtomProNet in Google. Then you'll see this link of the GitHub page. And here within this GitHub page, you will see this tutorial link. So you can just click in this link, you will get the same link for the training.
Anyone use machine learning in their research?
Yeah, I have.
Okay, that's good then.
Okay, perfect. I think right now, I hope it's installed. Let me just take a look. The first thing what we'll do here is that we'll try to download some data from material project. Okay, so for that, we'll go inside this bus folder, and then I'll take the folder path, copy path from here, and I'll just paste the path here. So once we do this, then the software will give you a few options. The first one is the data from materials project. I'll go for the option 1, and it's asking for the API. If you have an account in materials project, you can get the API for your account, but I already gave my one, so you just can click enter, and it should take my API, and then you can download the structure. It could be any structure. You can directly write down the formula, for example, alumina, or you can write the elements you want to download, for example, lithium, oxygen, manganese. For now, I'll just download a particular atomistic structure of alumina, which I know that is the structure of MP1938. I could have even said that I just want to download alumina. That will download the alumina structure also. So now it's asking that do I need the supercell? So generally we download the unit cell, but the supercell is the bigger structure of the same element. So I'll say yes, and then I want a 2 by 2 by 2 supercell to be downloaded. So now it will download a 2 by 2 by 2 supercell. It will take few time. Yeah. Now it's asking that do we need to download the energy and lattice data? We don't, because we'll generate them through the simulation. And okay, now it's already downloaded the structure. If we refresh the folders, we'll see there is a folder called VASP file. And then under the VASP file, you'll see there are two files. One is the unit cell and the one is the supercell for that structure. Okay. Done. Now we'll go for the second step. Second step is that we want to run some DFT simulation. So we can do the same process again. We can run the cell, and then we have to take the folder path. So we are taking the folder path where we downloaded all the structures, and go for the option 2. So this says the pre-processing for DFT simulation. So we go for the option 2. And so right now, this AtomProNet supports two different software. One is VASP, which is a commercial software, and the second one is Quantum Espresso, which is open source software. So you don't need a license for that. But I'm showing it for VASP, but the same process applies for Quantum Espresso also. So go for the option 1. Now, the first step we want to do is that we want to prepare the job submission folder. So we'll go for the option 1 again. And then now it's asking for, do we have the path where the multiple Postgres file stays? So we already have the path. So we go for the option 1, and then we give the path here. And that's it. If we go under VASP file, we'll see that there will be two different folders with all the required files needed to run the simulations. So there are other options also. Let's say we have a structure, we want to change its composition and try to see how the composition varies. That's something we are currently working on. But let's say we have a sample, we want to strain it in different direction to see how the structure behaves under loading. So we can do that. For example, if you go for hydrostatic loading, we can go for option 2, and we can just copy the folder path from here and just paste it. Okay, now it's asking for that what will be the range you required to strain the system. So by default it's given 5%. We can change it. We can say that yes, we want to change it, and then give a range of, let's say, minus like 2%. So that will be 0.02, and the step size is 0.01, and then the end would be 0.02 also. So if we do that and say yes, and then what we'll see that it will run all the file simulation file inside this folder. So these are the new simulation files with the strain data that we can run. Okay. Now, let's assume that because this simulation will take some time to complete and we cannot run them in a Colab because the software is not installed here. So let's assume that we have the folder. The only thing what we have to do that we have to submit this job and complete this job. So let's assume that we have the completed job. Now we want to visualize them. So if we run this cell, we'll be able to visualize them. So what I did is that I took a Illumina sample, the one we downloaded. I took a supercell, and then I strained it 10% in all directions, both compressive and tensile. So here, what you are saying is that this one is 10% compressive. This structure, the first structure is the 10% compressive structure. Then this one is 10% tensile structure. So you can see the gap between two atoms are increasing because we are trying to enlarge it. So the gap between two atoms will increase, and when we are trying to compress it, the gap will decrease, even though it's very minimal to see. But yeah, that's the structure. So and then there is one relaxed structure also. So just for visualization. Now, what we want to do is that we want to extract all of the information once we finish the simulation. So I already have the completed simulation here. So as you can see, I have 25 simulations completed. So what we have to do once the simulations are completed, we just have to again copy the path. We just have to give the path here. And then we'll go for option 3, pre-processing for neural network. So do you want to run the step? Yes, I want to run it. Again, I want to do it for VASP. And I want to go for option 1, which is self-consistent simulation. Okay, now it's asking for the folder path. I'm giving the folder path. And it already found that I have 25 structures. And if I refresh here, what we'll see that it already extracted all the energies, forces, lattice parameter data. So now it's asking that do you want to split it for the training? Yes, I want to split it. And by default, the file name would be converted.extxyz, but you can change it if you want. So you can just write option 1. And I want to split it in the test and validation data set. So now it's saying that you have 25 structure. How many of those structure you want to use for training of the neural network? So it's let's say 15. And then I'll use 5 of the structure for validation, and the rest of the 5 will be used for training. So now we have all the data required for the training. Now we'll do the training. So if we run this cell, we'll be able to see that here we have a Tesla T4 GPU with 15 gigabyte of memory. So now what we'll do is that we'll go for the next cell, and then we'll try to install the software which is required for the machine learning training. In the presentation, I have shown you that there are different steps. For example, you have to choose the descriptor, we have to choose the algorithm, then you'll be able to train the model, right? But there are different algorithms researchers have been developed. I'm here using the one which is called MACE. So this is pretty straightforward. You just these are uploaded in the PyP, so you can just install through pip install. So I have already written that you just have to run this cell, and then it will be installed within I hope within 1 minute. So we'll be able to see if it is installed or not. And so once it is installed, we can run the training with our test, train, and validation data set. And the next step will be try to visualize. Once the training is completed, we'll get the interatomic potential. We'll try to run some validation as I have shown you in the presentation, those parity plot and the cumulative distribution plot. Once the validation is done, then we'll go for the some molecular dynamics training. It will take some time, seems like, to install the software. In the meantime, feel free to ask me any question if you have.
Questions?
No, this is wizardry. Masana, you're a wizard.
Sorry, I couldn't hear that.
I said you're a wizard.
Oh, I'll take it as a compliment. Thank
Absolutely.
you. Yeah, so the installation is done. Now we'll do the training. So basically, this is the script for the training. Let's say if it is your first time, I would say that okay, take your time, go for this Colab tutorial. Just make sure that you are choosing the right GPU options before starting this Colab tutorial, and just go cell by cell, run all of this cell. You'll be able to get the exact result, same result what I am getting. So what it's doing here is that the training is started. So this is actually the training data file. So what it is doing here that you can see, just a second. You can see here that I mentioned the test, train and the validation file that we generated. Other than that, there are lots of options. You can change it if you want, or you can keep it as it is for now. For example, how many steps these training will go. We call that epoch. So here I am saying only 50 steps to make it to make the simulation shorter, not simulation, the training shorter. But in an actual scenario, you might go for a couple of hundreds of epochs. And also, these RMAXs define the atomistic structure radius. So within this 4 Armstrong radius, all the atoms will be trained in the same neighborhood. So how the atoms are behaving within these radius will affect each others. So if you can increase this value, that will make your potential much more accurate. But the downside is that it will be computationally expensive to use and also for training. And the other parameters is you can go to the MACE website and you can check what are the other parameter means. So what we are seeing here is that the training, once the training started, you can see that this is the initial epoch, and then we are going towards the total number of 50 epochs, and the loss is changing. The loss is obviously decreasing with every training step, and we have two parameters here. One is the RMSE of energy, and the second one is the RMSE of forces. So RMSE is root mean square error per atomic for the energy, and for the forces is the total forces of the system. So now it's around 19 step. I think it will take 2-3 more minutes to complete this training. Once the training is done, we'll get the interatomic potential for using. Let me just take a look where it's saving. Yeah. So as you can see, there is a new folder generated called MACE model, and under this folder, it will be saving the potential files it is going to generate. So it will take maybe a couple of more minutes.
Musanna, do you need to know some specific language background to be able to use this platform?
Not really. That's
R.
the idea here. Yeah, please continue. Yeah, so what I was trying to say is that not really. For example, for the experimentalists who are not in this field but want to start digging into it, you can just, as simple it is, you just install this software. Basically, you need to give some folder paths, and you have to choose some options. There are a couple of steps. Maybe at first it will be overwhelming to understand these many of steps, but you don't need to learn a new language, or you don't need to have a very deep understanding how all of this algorithm works. Without doing that, you can train in potential and try to see how it works. So the idea is that the researchers can use most of their time to solve a problem, to understand the physics of a problem in an atomistic viewpoint, rather than spending more time on pre and post processing
Yeah.
what we are trying to do. Yeah.
Is
So
it like is it like more like developed library? There are different pieces. It's like Lego, and then you just use the ones is necessary to make your final model. What you are trying to model is something like that.
you are correct. So there are a couple of modules, I would say, in this software, which is linked to the machine learning potential. So you can use whichever you required for your case. So there are so many steps. The reason behind is that this problem contains different level of expertise. One is quantum mechanics data extraction, then doing the machine learning potential, and then doing the classical molecular dynamics simulation. That's why it looks like there are a lot of steps, but to be honest, this actually compresses a lot of, I would say, hard work in the background, so that you can just follow this step, use the modules that you required, and you can build the machine learning interatomic potential. With that, I would say that, yeah, our training is done. Close to finish here. Now it's evaluating, and I think, yeah, it's done. Perfect. So now we have an interatomic potential. So if you look here, you'll see that what are the errors in root mean square value for the forces energies. So it's a quite high value, I would say, but yeah, we are using only 25 atomistic structure for 50 simulation step, sorry, 50 training steps. So we should not expect higher accuracy than that. So if you look in this folder, you'd see that this model file, this is the trained neural network file. So now what we have to do is that we have to evaluate this file. So I'll just run this file, run this step. So what this step is doing is that it will try to generate the file through which we can do the parity plot, that through which we will be able to test the values. Okay. What happened? Content. Oh, I made a mistake. Sorry. So I just have to remove this. Oh, perfect. It's done. Now the next step is that we'll try to visualize the parity plot. For that, we just need the folder path from here. Go to example dataset, data extract. Yeah, so we just need the folder path here, copy path. And then we go for the option 4 and go for what we are trying to do, post-processing of MLIP that we generated. Now it will be asking me for the folder path. This is the folder path and the dataset name. So the initial true dataset name is the one we generated before, which is validation.ext xyz. And the second one is the MACE validation, which is generated through the neural network potential. MACE validation.ext xyz. So now it will extract all the information of the energy and forces and will do some plot for us. Okay, perfect. It's done. Now we can do the plotting. Yeah. So so now it generates all the plots, the parity plot and the cumulative distribution plot. So here you can see these dots are basically the predicted RMS forces, and these are the R square value is not too close to 1, but it's not bad, I would say, with only 50 epochs. And you can see that 90% of data is under the force error of 0.128. Same for the energies. Now we want to do some classical MD simulation with millions of atoms. Right now, we'll not do that, but the idea is that we'll be able to run this machine learning potential for millions of atoms and to understand the physics of a problem of different battery systems. So for that, first step is to that we have to generate a LAMS compatible MLIP format. It's already done. Once we run this, and then the next step is to install the software called LAMP. So here I included all of the instruction requests to install the LAMPs with different packages. You just have to run this cell, nothing more than that. But it will take some time to install, probably 10 minutes actually. So I'll keep it running. But in the meantime, I'll go back to my slides and I'll move to the next slide. So now I'd request everyone, if you can please scan this QR code and fill the survey. It might take 5 to 7 minutes to fill this survey while the software is installing.
Musanna, is there similar platforms, not necessarily for the atomistic simulation, which is your research topic, some other areas from the same source?
I mean, there are different neural network training methods that can be applied for different systems. But specifically, I can say only for the atomistic simulation. But do you have anything in mind? What kind of?
No, I was thinking more our researchers, like we have, not everybody is on the technical side. We have people working on the cluster, especially like socioeconomics, more I would say like probably logistics,
Mhm.
like supply chain logistics type of. I'm sure LCA guys, they have their own software. I don't know how much machine learning you guys are using.
No, for life cycle thinking, we don't do it. Because we use Simaku and other software,
Yeah.
so they have like a large database.
Yes, they have their own
But
library.
for data analytics, like if we have some prediction problems, so then we utilize machine learning techniques like classical and advanced, like in similar methods. Sometimes like deep learnings, like Musamma is working like it's too advanced. But
Yes.
you are more rely on convolutional LSTM and kind of stuff.
Okay.
Yeah, I mean, that's true. Like there are different kind of algorithms for different applications.
But sometimes it depends. Like it's all about your data set. Sometimes
I realized halfway through.
if your data is like this some insights, so you can't go for like deep
Like a
learning.
month ago.
Yeah, if it is like large data sets, then you
Really?
can consider like deep learning models.
Yes, yeah.
Yeah, like if
Otherwise, we will use Excel, I guess.
no, we can use machine learning.
Yes.
But for large data sets, like big data sets, so we go
Yes.
for deep learning. Like sometime now, like LLM.
Okay. I just wonder, yeah.
So we are unable to scan the QR code.
I did.
Yeah, we are unable to do that. Can you please zoom in the code?
Oh, sure. I'll just share the screen. Is it good?
Okay, we are trying.
No. That'll be hard for you to manage the
It's done for me.
zooming. Oh, it works.
Thanks.
Mhm.
Is it working?
I think for some
I'm done.
people, sometimes could be.
$50 gift card.
How many winners? We don't.
When do you announce them? When's the survey close?
Sorry.
When does the survey close?
I'm not sure. Maybe next month.
Okay, because you've had it open a bit, right?
It's open for a bit, yeah. But the response it's very difficult to get responses,
Yeah, I
especially.
realized halfway through I'd already done it.
No, that's the winner.
Yeah, I mean, I got a lot of response, but I'm assuming a lot of them are AI generated or spam.
Oh,
And
wow.
I have to filter them out. Yeah.
Oh, that's challenging. How do you identify them? Like if it's real?
Yeah, I mean that's another research topic for me. One thing is that the IP address, from same IP address, there are multiple submissions, which doesn't make sense at all, like even the responses. And then the second thing is that the platform I'm using, Qualtrics, they have geolocation data. So the geolocation data and the location they mentioned, these are not matching
Okay.
for the fake ones. So
Okay.
yeah.
Good point. Good to know, really. While we are waiting, can I ask Pranab for next month's presentation? You confirmed?
Yeah, I can do it on the review paper.
Yes. I think we said around maybe 24th, April 24th. We do pretty much like the third Thursday of the month. So then I will send the invite. I think for May, we will skip because we will have this in-person cluster meeting. There will be some student presentations. And probably after that, June. We may have a break, July, August, I don't know. I will check with the PIs. I may need probably one more presentation for June. I don't know if we have any volunteers. Yes, yeah. Amir, you're Amir. You joined the team, I think, recently.
Yes.
But I remember receiving emails from you when you were back home trying to get your visa,
Yes,
I
yes.
think, yes. Are you working on literature review too?
Yes, I'm working on it.
Okay, maybe we can, let's see what material you will have. I think it's about additive manufacturing.
Yes.
Okay. Maybe I can connect with you to find out if you have enough material for June presentation, like the end of June.
Yes, of course.
Yes, okay, I will. Okay, good. Then May break, and then Pranav will do in April, and then maybe I will ask you for June. Good. Thanks.
Right? Yeah, no, I
After
noticed
that, yeah.
that Lieutenant Donahue answered the question. He had a different response. Because the first time I did.
Okay, you guys have a few.
And simulation, so I put slightly familiar, and I got to the next one and listed. Software, I'm like, I don't know. Don't know at all. But it's like, would you like to look?
No.
Yeah. 74% will take maybe 2-3 months more to install. Perfect. So the installation is done. Took around 11 minutes. I'll not take more than 1 or 2 minutes. I'll finish the presentation soon. So the next step is that, okay, we already installed the classical molecular dynamics software. We already trained our model. We have the training file with us. So what we will do right now, we'll try to create the input and data script. If we try to visualize this, it should be maybe outside of this file. Yeah, perfect. So basically, see, this is an Illumina structure, but this structure we want to test through classical MD. So instead of this structure, we can use millions of atoms in MD because this is going through linear scaling. But the potential we actually trained using the DFT data for the Illumina structure I have shown before. So let's do the training here. And what we are trying to do here is we are trying to get the cohesive energy of a system. So the cohesive energy means, let's say there are two atoms, one is aluminum and one is oxygen, which are bonded to each other. How much energy will be required to break that bond? So yeah, it's already done. So if we come here, we'll see that the number of atoms in the structure was 20. And the cohesive energy value, what we found is that minus 7.42 eV. And if you look here, I have the standard data from the DFT cohesive energy, which is minus 3.97. And these are from other methods. So even with only 25 structures and 25 structure and 50 epochs, we get a very close result with this interatomic potential. So I think it has a huge potential to apply on the researches what we are doing in the battery field to study complex battery system to understand it better. For example, the last year, the work we have done with Professor Liu's group on NVPF material. For that, I forgot the exact number, but I spent maybe 1,000 CPU hours just to understand the NEB path. But if we could do that, the NEB path means how the ions are moving. But if we could build an interatomic potential and try to understand it, it might take less CPU hours. Not only that, it could be faster, and we could do more analysis with that. With that, I'd like to finish my presentation and my tutorial, and I'd be happy to answer if you have any question.
Okay. Thanks, Musana. It's lots to digest, I think. Yes. But I think the message is we can see the potential when we'll compare it to numbers and the amount of time and input you put and what we are getting out of this work is clearly as the potential. You don't need to spend probably 1,000 hours of speed time you mentioned.
Yeah, I mean, the idea was that basically for someone who is not from actually this field to give an overall idea how these things work, like the idea of today's presentation, and how they can think about their problem, and then somehow maybe someone will help them, or they can spend some time on these softwares. I think it will be pretty straightforward to implement and get some optimistic results.
Thank you. Do we have any questions from the room?
Yeah, sure. I have one. Ms. Sana, really impressive intersection of both programming knowledge and atomic level understanding. I was curious if you could give us a more definitive example of how to apply this to a research problem itself.
First of all, thank you. And so let's say we want to understand the ionic migration during charging. So if we want to do that, the current, if we don't do machine learning, what we have to do is that we have to do quantum mechanics, probably DFT. We have to take different structure. This we call images. So what we'll do that let's say we'll take 10 different images of different positions of the ion on that cell on the cathode, let's say, and then we'll explicitly simulate that to understand what are the energy barriers it's facing. Now, as I said, it's quite expensive, and this is only one data point you will get from this. But if we do some high quality simulations and take this data and train the model and then use that model, then you will be able to study in the actual length scale of, I don't know, like maybe a couple of 100 nanometers, the thickness of the cathode layer actually we are using in our battery, to see how it goes all over that path. So that could be one example. Other could be studying the ACI formation over the batteries. We can run it for longer time and try to see how the surface will evolve with time and form the ACI. Other could be studying the dendrite formation even. These are the possibilities. I mean, there are not enough studies, but this opens the possibility to study all of these things in the actual atomistic scale. Right now, what we are trying to do is that we are trying to overlap different scale. We're trying to create a multi-scale model. Why? Because we don't have the capability to understand the dendrite in the atomistic cell. So that's why we're going for mesoscale method like phase field, where the scale is higher in the micrometer range. So I think that gives some information about your question.
Yeah, great. Thank you.
Any other? Okay, I think thanks. We are also on time, and my apologies. I was a bit late at the beginning. So what we are going to have, I think next Pranab will give us a presentation about his literature review. I think it's on the different recycling technologies for batteries. So I will send the invite. I'm thinking about April 24th, I think, on Thursday. It's like I'm trying to stick to like third Thursday of every month. And in May, we will have in-person meeting in Kelowna. I'm not sure if I send the invite to students, but if not, I will check and I will do it. So you can start to plan your trip. Amardeep, I don't know if you can make it, and Musana, but that would be great. And then, yeah, we will, after May, probably June, we may have maybe Amir to give a presentation. Thank you all for joining us today, and I will finish the recording and then share with Jen, I think. Thanks, Musana.
Thank you. Thank you, everyone.
Have a good day.
Bye.
Bye.
Right to the left.
I don't
Just pause and stop recording. Right to the left.
Yeah, I don't know.
Where is it?
The coding.
Oh, yeah.
There or right there.